Thanks, Paul-André, and thanks to the organizers for inviting me. So I'd like to talk about Mezzo in two lectures. So this is work by Jonathan Protsenko, mainly, who is my PhD student, and also the other people listed here, and myself. So today I'd like to explain what Mezzo is using examples, what's the motivation, what it looks like, what we're trying to achieve. And tomorrow, time permitting, I will try to go into the more theoretical aspects. How do you prove that this programming language is type safe? And this is a proof that we have mechanized in Coq. So today I'll begin with an example. Before trying to say anything general about our goals, I will begin with an example, which is a simple example involving write-once references. And so I will use this to show what we can do and cannot do in Mezzo, what the type checker is able to express, and then I will go back to general design principles and motivation. So, as you can guess, a write-once reference. So it's a reference, which means a memory cell in ML parlance. And it's supposed to be written at most once. So initially, it's uninitialized. It does not contain any useful value. You're supposed to write it once, and then you can read it as many times as you want once it has been initialized. And this can be useful in some practical scenarios. So this is a type which is not primitive in Mezzo. It can be defined by the user. We'll see how later, but first I'm going to assume it has been defined and show how it's used to begin. So if we open this module of write-once references, then we can create new references. So R1 is a new one, a new reference. And after this definition, the type checker knows that R1 has type writable. So I'm using this at notation, which we'll see many times in the talk, which is what I call a permission. So this means we have permission to use R1 as something of type writable. We can also give it a new name. We can also call it R2. And so if we do that, then we have two names for the same object. And the type checker must keep track of the fact that it's the same object, because if we were to see this as two different writable objects, then we would be allowed to write twice. So the type checker at this point will know that R2 is an alias for R1, and we still have just one permission to write. So we can do that, actually. We can write. There is a set function which we can call to write R1. And we'll see that this permission here will be replaced. The type checker will keep track of the fact that R1 is now frozen. So there is another type called frozen, which is parameterized with the content. So here we are writing an integer value. So R1 becomes a frozen reference with integer content. And we still have R2 equals R1. This fact hasn't changed and will actually never change, because these are immutable variables. R1 and R2 are immutable variables. And once we have done that, we can read R2, for instance. We could also read R1. It would be the same thing. And the type checker knows that this gives us an integer value and does not modify the facts that we had before. So here it knows that it's OK to read R2 because R2 is equal to R1 and R1 is a frozen reference. So R2 must also be a frozen reference. So that's the kind of reasoning that we would like the type checker to perform. And as a final example of what we can do, we can also alias an object. Here I have aliased R1 and R2. I have created a pair of these two things. And at first, the type checker gives this pair a very precise type. It has the type pair of exactly R1 and R2. And if we want, we can also say that this is a pair of two frozen references. If we do this, we forget the fact that these are really the same reference. But it's OK to forget in this case, because frozen is a type. It's a duplicable type. That's the word I will use. It's not an affine type like writable, where we must have only one permission to write. So that's the kind of thing you can do in this language. And I have drawn this little state chart trying to say that we have two states. A reference is in one of two states, and we have some transitions between them. So new, set, and get are user-defined functions. And this funny arrow here is supposed to mean that when you have a frozen thing, you can implicitly duplicate it, as I have done in the final line. So the kind of things which you cannot do, I could show briefly using Emacs. For instance, here, at the beginning, I have defined R1 as a new writable reference. If I try to read it immediately before writing it, then I will get a type error message. And you will see, well, let me zoom on that message. So it's a horrible thing because at the moment we have what we could call a prototype type checker. So it prints the whole explanation of why this thing failed. But Jonathan has done some good work. And below we can find a tentative shortened explanation, which in this case is pretty good, I think. It says basically you cannot get R1 because we do not have the permission R1 at frozen, which is reasonable. So in this case, with some extra effort, we could print a reasonable message. Oh, I should say, if you want to ask questions during the talk, that's fine with me. So do not hesitate to interrupt. And there are other examples of things you cannot do in here. For instance, once you have defined R2 as equal to R1, you cannot pretend that you have two writable things. That's not the same as saying I have a writable thing and R2 is equal to it. Yes?
These assertions fail at runtime?
No, so the assert here is a static assert. Okay. Yeah. So this is a claim which the type checker has to verify statically. So here it says it's true that we have this situation, but it doesn't imply that, which would mean that the two are distinct. So this star is like separation logic conjunction. It's separating by default.
Do you swap R1 and R2 in that example?
What do you mean by swapping?
Assert R2 at writable and R1 equals to R2.
Oh yes, equality is as usual. It's symmetric, reflexive, transitive. So this works, and you would want to say R2 here. This should work too. Yes, yes. So. So it's able to make deductions. As long as equality is involved like this, it's okay. So these files are online on my web page, so I guess I will not read all of it, but I have inserted some examples of what's possible and what's not possible in here. So going back to the slides. Demo, that's done. So what are we trying to do? So through this example, you just had a very small idea of what we're trying to do. We're trying to do something that's very much like a program logic in a sense. We're trying to disguise it as a type system, but it's very much like separation logic. It's a flow-sensitive discipline where the type of a variable changes with every program point. And actually, there is not even, I shouldn't say the type of a variable, because a variable could have 0, 1, or more types. You could have several permissions for the same variable, or you could have no permission at all. So things change as you step through the program text, and you can have several permissions. And these things are like separation logic assertions. They have a double reading. They tell you about the layout of things in memory, and they also tell you about ownership or about what you can do with your variables. So R at writable, for instance, has a double reading. You could say this means that at address R in memory there is a memory cell, but it also means I am the owner of that memory cell since I am the only one who has this permission to write. So there is always this double reading, and that's what people call ownership is in the eye of the beholder in separation logic. So if you know the type of something, it means you own it in a certain way. And as we saw with the example, we had this type writable, which was affine, and the type frozen, which was duplicable. So these are the two basic modes. And we wanted the system to be simple in this respect. So we didn't go to more complicated things like fractional permissions and so on. So we just chose to have these two modes. And by default, you can declare your data structures as either immutable or mutable. And by default, immutable data will be duplicable, so everyone has access to it. You can share an immutable data structure, and mutable data has a unique owner. So that's the basic discipline, which is simple and quite restrictive. But we will see that there are ways of escaping these restrictions. And you saw in the example that we have these equations. So when you define an alias using this syntax, the type checker does exactly the same. It defines an alias internally. So it does not say the type of y is the same as the type of x. It says directly y is equal to x, and that's more precise. So these are singleton types technically. That's what you could say. And it means once the type checker knows that two names mean the same thing, you can use these names interchangeably in your program code. And as we will see later on, this works also for accesses to fields, for instance. So if I define this, then in the dots, I can say either x or x's.head, and they mean the same thing. I can use one or the other. It doesn't make any difference for the type checker.
Before, when you were writing R1 is equal to R2, it was sugar for this?
So val is a top-level let definition. So when I say val R1 equals R2, it was basically the same as let x equals y.
And then the permission in the assertions.
Oh, in the assertions. Yeah, so x equals y in the assertion is sugar for x at singleton y. So far we have just one form of permission, which is x at t, where t is a type. And yes?
You cannot share mutable data.
Well, you can copy a value, as I will say very shortly, but you cannot copy the permission. Yeah. I have some more slides about this coming up next, I think. Yeah, these are exactly the next slides. So it's always OK to copy a value. This does not create any problem for the type checker because it has the necessary vocabulary to keep track of what you're doing. So if you say y is a pair of x and x, the type checker says, OK, y has type pair of singleton type x and singleton type x. And that's the most precise description possible. So no problem so far. Even if you don't know what the type of x is, you're still allowed to write that. Now, if you do know what the type of x is, then you can make further deductions. For instance, if I know that initially I have the permission x at int, then I get this situation where initially I know x at int, and after this let binding, I still know x at int. It's been framed, if you will, on top of the previous slide. And I also have this new permission, which is created by the let binding. And now I can do some reasoning. By combining these two things, the type checker can implicitly deduce that y is a pair of two integers. So if you try to use y as a pair of integers, it's going to be accepted. And the same would not work if x was something which is not duplicable. So if you know that x is a reference to an integer, references have a unique owner, so to speak. Or in other words, the type refint is affine, which means that we have this, that's fine, but we cannot deduce that y is a pair of references, because that would implicitly mean a pair of two distinct references. So if you write this static assertion, it's going to be rejected at compile time. So that, I guess, answers your question. By default, you cannot share mutable data in that sense. Yeah, so here I have a few examples of things that are duplicable or affine. We will see later on the definitions of list and mlist, but list is just the usual immutable list. So if you have a list of integers, it can be freely shared, just like in ML. If you have a permission such as x equals y, So this is sugar for x at equals y. This is duplicable because our variables are like ML variables. They're not mutable. So if an equality between two variables is true at some point, it will be true forever. And so it's OK to share that equality. And these things here represent data structures which are partly mutable and partly immutable. So this is an immutable list of mutable things. And this is the converse, an immutable list of immutable things. So these things have to be viewed as affine because they give exclusive access to at least part of the heap. So for every permission, the type checker can tell automatically whether it's duplicable or affine. So the programmer doesn't have to worry too much about it, except when the type checker refuses to do something, then you have to understand why. So we saw that already. Conjunction is separating because ref is affine. It's saying the same thing, really. Because ref is affine, this conjunction means that x and y cannot be the same location. So it's two sides of the same coin, saying that a permission is affine and saying that star is separating. And the same thing for pairs. The interpretation of pairs is given by this decomposition law. If you know that Z is a pair of something of type T and something of type U, it really means that you could name the two components of the pair and say that separately you have permission for X at T and Y at U. And this implies that, because conjunction is separating, this means that product is also separating. And the same will be true for algebraic data structures in general. We will see lists later on. They're defined using products like this, so they are separating too. If you have a list of references, by default it means a list of distinct references. So why are we doing this? You may be able to make a good guess, I hope, but I still have a few slides about that. So you know that the types of the mainstream, so to speak, programming languages usually describe the structure of data, but do not say much about ownership or permission to make changes to data. And also, they don't distinguish between trees and graphs. They don't say anything about aliasing. So the goal is to be more ambitious in that respect and try to make more distinctions, and as a result, possibly roll out some errors and make some new programming idioms possible, which were not possible before. So things that we can rule out are data races in a concurrent setting. So this is pretty important, I think. And we will see examples of that later on. And also more subtle errors like representation exposure, which means that you're leaking a pointer to a data structure which was supposed to be private. So someone will be able to modify the internal representation of your object without you realizing it. In Java, for instance, there have been bugs in the standard library based on this kind of mistake. And also, data races, that's when two different threads try to read and write the same place in memory at the same time. So it means you don't have proper synchronization. And here, data races will be ruled out for a very simple reason, which is that whenever you want to write, you need to prove that you are the unique owner. And this means no one else can either read or write. So it's almost trivial that you cannot have any data races when you have such a type discipline. What's non-trivial is why the type discipline is not too restrictive. But this side is relatively trivial. And here are some new things which we can make possible. I guess maybe it's more interesting to be able to rule out errors, but still there are a few things which you could not do before and which you can hope to do in this kind of language. One is to explicitly reuse memory when you have a record which you don't need anymore and you would like to allocate a new record which happens to have the same size, for instance, then you can reuse the old memory because you know you're the only owner. You can also do gradual initialization, as we saw in the example of write-once references. And also, using write-once references, we saw that you can describe some protocols. You can explain that you're supposed to call set first, and then you will be allowed to call get, but not the other way around. And you can hope to describe more complex object protocols in the same style. So this is a rather restrictive discipline, as you may guess, mainly because it's not allowed to share mutable data by default. So one answer is that there is no restriction on immutable data. So if you're already convinced that functional programming is the way to go, then that's great, because you can just ignore the restriction and continue to program without mutable state. And otherwise, if you do need mutable state in a few places, then there are several ways which I will try to explain today, if time permits. Several ways of sharing mutable data. And yeah, the even less pleasant thing is that there are some things that become very, very unpleasant when you have such a type discipline, like trying to look up an element in a container. So a container could be a hash table, for instance, some kind of dictionary. You would like to call the lookup function to find the data associated with some key. And once you do that, the lookup function returns a pointer to you. So you have two aliases for this data now. You have one that's still accessible via the dictionary, and another that's accessible via the pointer returned by the lookup function. And so by default, you're going to be in trouble if the element has an affine type. You could either say that lookup returns the permission to use the element to the caller, but then your dictionary becomes unusable. Or you could say that the dictionary must remain usable, but in that case, lookup returns an unusable value. Or you have to try to explain that the dictionary remains usable, but only for looking up other keys, not the key that was just looked up. So it's tricky. And the solution to this problem is to go back to the workarounds that I mentioned on the previous slide. So basically, you must not have a dictionary that contains affine elements, or you will be in trouble. So what we do is we build dictionaries that contain duplicable elements, because the previous workarounds that I mentioned are ways for an affine element to masquerade as a duplicable one. So this allows you to work around the problems. But maybe I'm saying too much ahead, and I should present these things, and we can talk later about the problems that remain. So to conclude this introduction, I would like to say a bit more about write-once references. I showed briefly how they're used, but now I would also like to show how they're implemented. Since they're a user-defined type, there is nothing magic about them. And if we see how they're implemented, we will have an idea of what kind of things you can do in this language. So the small state chart that I drew basically has types as the states and user-defined functions as the transitions between them. Here we had two states, writable and frozen. So what I'm showing is the interface file for this module. We have a simple-minded system of compilation units, which is like OCaml or Camel Lights, if you will. So whenever you write a compilation unit, you have to write two files. The MZ file contains the code, and the MZI file contains the interface, the type of every value. So this is the interface which the programmer would write, where we declare that we have two abstract types. So that's one state of the state diagram, if you will. I hope this is readable. And that's another state. Frozen is another state. And what I'm doing here is I'm declaring that frozen is a duplicable type. this is something I have to declare in the interface of the module. I don't declare any such thing about writable, so the type writable by default will be viewed as affine by the type checker. And here I'm just declaring that frozen is duplicable, but in the implementation file we will see how frozen is defined, and the type checker will be able to verify that the definition of frozen is actually a duplicable type. So this is not an axiom, it's a declaration that is checked by the type checker. And then we have these three user-defined functions, which we have seen already. And now we see that types. So new takes no argument and returns something of type writable, which means that it really returns a fresh thing of type writable. Because if I write, as before, if I write val r equals new, call to new, then after this call I will get a new permission r at writable. And this permission will come in addition to whatever I had before. So if before I knew that I had some permission p, then afterwards I will have p star r at writable. And since star is separating, this really means that I have a new reference, a fresh one. So it's easy to say that a result is fresh. It's actually less easy to say that something is not fresh. That's where sharing comes into play, and it's trickier. In the case of the set function, set takes two arguments. We saw before the call to set r, 3, for instance. So at runtime, it takes just two arguments. But conceptually, at compile time, you have to pass some permissions. So for instance, this r colon writable here means that you have to pass two things, if you will. At runtime, you have to pass the parameter r. And at compile time, you have to prove that r has type writable. Or in other words, you have to pass this permission r at writable, which doesn't exist at runtime, but you can think as if you were passing two things to the function. That's a good way of thinking about it. And here there is this consumes keyword, which means that the permission r at writable, which you have to pass to set, will not be returned. So our convention is that if you don't say anything, the permission is returned, and if you say consumes, then it's not returned. So concerning x, for instance, I don't know if I have a bubble about that. No. Concerning x, this means you have to pass the value x at runtime, and you have to pass the permission x at a. And since I did not write consumes, the permission x at a is returned in this case. And why does that make sense? Yeah, here for simplicity, I have restricted this function set to the case where a is a duplicable type. This makes my example somewhat easier to explain. And it also allows me to point out that duplicable a, so this is an assertion that a is a duplicable type, and it's itself viewed as a permission. So here the caller is requested to prove that a is a duplicable type. And that's a proof that happens at compile time again. And in the result, the function returns nothing at runtime. So this is a slightly sugared syntax for saying unit conjunction this permission. So it returns unit no result at runtime. But at compile time, if you will, it returns the permission r at frozen a. So after the call, we know that r has become a frozen permission. Frozen reference, sorry. So we have transitioned from one state to another because we have lost r at writable, and in return we gain r at frozen a. And finally, in the type of get, get requires the argument to be frozen and doesn't consume this permission. But it doesn't really matter in this case whether there is a consumes here or not, because frozen is a duplicable type, and something that's duplicable is never consumed. You could consume it, but you could also make a copy of it before consuming it. So in the end, it's not consumed. Are there any questions?
Just a kind of trivial question. Does the initial state not count as a state?
Well, anything I say about states is informal anyway. So the only formal aspect is the text, the program text on the slide. So I don't know. I guess your question has to do with what's here, and is it the initial state, or?
I mean, you can be in one of. When you drew the state.
Yes.
I could go back to it, but it was okay. Yeah, basically, a write-once reference has to be in one of those two states. There are no other states here that it could be in.
Okay, when you create it.
When you create it, it's writable. Yeah. And then you set it, and it's frozen, and there are no other states. But we could potentially create types that have more, well, data structures that have more complex transition diagrams.
Maybe a question is, can you always associate the state diagram to your declarations?
I guess not. I mean, it's in the easy cases, you see a kind of correspondence between the types and a visual presentation. But you could also write some very complex types that don't have a clear visual representation. Okay, so that's the interface file. And then the implementation, well, there isn't much to say about it, but here I'm declaring writable as a record with one field. And initially, when the reference is allocated, it doesn't contain any useful value, so I'm just using a field of type unit, which is meant to be later mutated, later written. So I'm declaring this type to be mutable, which implicitly means it's also affine. It has a unique owner. And I'm declaring frozen to be immutable just by omitting the mutable keyword. So frozen also has one field, which has type A, and for slightly technical reasons, I'm requesting A to be a duplicable type. And that's a piece of information which is conceptually stored in the field together with the value. So new is just allocation. So that's the syntax for creating a new object. So that's the tagger, the data constructor, if you will. And this is the list of fields with their values. And, well, the set function basically writes x into r.contents. And there is, I could explain a few things about how set is type checked. It's going to be type checked basically by symbolic execution, if you will, or by stepping through the program text and keeping track at each point of the permissions that are available. So at the beginning, when we begin executing a call to set, we have r at writable, and we also have x at a. These are the two permissions that we have. We also have duplicable a. So in particular, r at writable, and we can unfold the definition of the type writable, and we can also write what we know about R in this form, which means we know it's a memory block whose tag is writable and which has one field containing a unit value. So that's what I call a structural permission. It describes the memory block. And we have a simple memory model where every block has a tag and a list of fields. So once we know this, it's fairly clear that the write instruction here is safe. It's going to write x into the contents field. And we will get a new permission after this instruction. I guess you can guess what the new permission is going to be. We are going to have just one slight change. Just change unit here to equal x. And that's, again, the most precise description possible. We know that the new value of the contents field is x, so its type is equal x. The singleton type whose only value is x. And now that we have this, we also have x at a, as I said earlier, so we can combine these two things. If you know that r.contents is x, and if you know that x has type a, then you can combine these two permissions to get this, which may look more familiar, and says the contents field has type A. And when you do that, you consume X at A. So you would consume it if it wasn't duplicable. In this case, it is duplicable.
So sometimes you say X at A, and sometimes X has type A.
Yeah, so X has type A is my informal, it's purely informal speech, but it's always X at A. So yeah, when I say X has type A, you should understand I have permission X at A. That's what I really mean.
And that's X colon A.
Sorry?
And that is X colon A?
Oh, yeah. Then there is a slight distinction between at and colon. Colon is a binder, and it's used in function headers. So this binds X, and this binds R. Whereas when I write this, it doesn't bind X. It's a reference to some variable X that was bound earlier. I could show this in the type on the previous slide. If I show the type of set, here I have R colon and R at, because here I am naming R the first parameter of the function. So that's a binder. Whereas this is a reference to the R which was introduced on the previous line. So yeah, I could explain this another way by going to a buffer and saying, let's see, scratch. When I say, yeah, that a function requires R at type writable, I could also say that it requires something of type singleton R, and it requires the permission R at writable. And then if I do this, I have two free occurrences of R, so I need to bind it somewhere, and I can bind it by quantifying universally. We have a way of saying that. Yeah, so here I'm saying for all value R, the function f expects something of singleton type equals R, and it expects the permission R at writable. So the colon syntax can be viewed as syntactic sugar for this more complex thing below. But yeah, sorry?
The motivation, if I would now replace in the ampersand with a colon, then I would bind a new R.
Yeah, so this thing up there is a binder, and this too is a binder, and these two are free occurrences. They're references to earlier binders.
Yeah, I was trying to understand what's the motivation of using two different symbols. Is there the danger that in some place you could write either ampersand or colon and it makes a difference?
Well, the type of set, I think, shows the motivation. Oh, sorry, I went to the wrong program. The type of set shows the motivation. Here, I really need to say, I'm really saying two different things. In the first line, I'm saying, give me any reference, and let me call it R. So I'm binding the name R. But in the second line, I'm saying, after the call to set, the reference R will have type frozen A. So I'm referring to the earlier R.
I understand, but usually you write the assumptions, the hypothetical judgments and judgment in the same syntax, right? I mean, in programming, I write x colon int when I bind it, and later I write, if I want to say that x has type int, I write x colon int again. But you do it different. I just don't understand what the motivation is.
Well, I guess I didn't want to overload the colon. I mean, if we could, syntactically, we could try to write a colon here, but it would be interpreted as rebinding a new R in the result type of the function. So
you can bind anywhere the R also in the result type.
Yeah, you can also bind things in the result type. So let's go back to this. I could write a function type that looks like this. Sorry, colon. And this would be interpreted basically as pi sigma. So this means for all argument x, the function returns some result which you can call y. So if I do that, I have two.
It will make a difference because it takes a colon with the ampersand.
Oh yes, it makes a difference. If I say something like this, then it means some variable y, which was bound earlier, is guaranteed to have type int when the function returns. So we do need a distinction between colon and at.
Again, this can be decomposed into
Yeah, the colon can be desugared into simpler things. And tomorrow, when I speak about the theory, we will see that in the theory there is no colon operator because it's desugared into simpler things.
So you can continue permissions here, but for non-duplicable permissions, does it make sense to have them twice or 3 times? Can you duplicate them? I mean, so can you say that I consume this permission 3 times and generate twice?
Well, duplication is always implicit. So when you have a duplicable thing,
No, a non-duplicable.
oh, non-duplicable thing.
So does the multiplicity count? You can count them between the 2 types.
You cannot count. There is no counting. And no, so you just have one copy. If I have r at writable, if I give it to a function that consumes it, then I lose it. And I cannot have 2 copies of it. Okay, so I was commenting this. Yeah, here we fold this and we get writable with a contents field which has type A. And now, so this is a kind of weird thing. This is an intermediate state, really, because it doesn't match any of the 2 type definitions that are here. This one says the tag should be writable, but the contents should have type unit. And this one says the tag should be frozen, and the contents should have type A. And here we are in between the 2 states, because we are in between 2 assignments, really. So that's why I'm going to do the second assignment. Here we have this slightly weird instruction which doesn't exist in OCaml, for instance, where it's permitted to write the tag of a memory block. After all, it's just a field, almost like any other field. So it's permitted to write a new tag into it. And here I'm writing the tag frozen into it.
But that comment is not.
Yeah, the comment is true, actually, because if you think of what happens at runtime, this tag is encoded as the integer 0, and this one is also 0. So actually, at runtime, nothing happens, and this instruction is completely erased. So you can think of this instruction as a hint to the type checker. It really means now you should view this cell as a frozen cell. It doesn't do anything at runtime.
Where can I change the tag?
Sorry?
Where can I change the tag?
Where?
Where can I change the tag? I mean, you're writing the tag here. Can I do it at any?
Yeah, basically at any time, provided you are the unique owner of the memory block, then you can change its tag to basically whatever you please. We have 2 restrictions. One is that initially the memory block must be mutable, obviously. And the other is that you must not change the number of fields of the block. So you cannot go from a tag which implies 2 fields to some tag which implies 3 fields, for instance, because the runtime system doesn't allow adding or removing fields. But otherwise, it's okay to do this.
You don't have to define a set of tags that you could switch between?
No, you can go from one type to a completely unrelated type, as long as they have the same size in memory, basically.
When you say the number of fields of the tag, is it defined? Is it a characteristic of the tag, or does it happen uniformly that you check that
It happens when you type check the tag update instruction. We check that the old tag and the new tag imply the same number of fields. So the size of the block doesn't change in memory.
But the writable tag we have here is not the writable tag of the writable definition.
What do you mean? So here we know that the old tag is writable, and we know that the new tag is frozen. So we go to these two definitions, and we check that they both imply one field. So the update is permitted. And by the way, that's the reason why I put this field of type unit here. Otherwise, I could have put no field at all, but then the tag update instruction wouldn't have been permitted. Yeah, so you can do some weird things, for instance, like recycling continuations. There is a paper by this title by Dan Friedman and someone else where you need to allocate a memory block of size 2 when you happen to have one such block at hand, and it doesn't have the same type, but it doesn't matter, you just reuse it. So that's something you can do here. Okay. So basically, at the end of this 2-line piece of code, the type checker is able to prove that R has type frozen A, by which I mean we have permission R at frozen A.
But only because we know it's duplicable, yeah?
Yeah, in this case we need to duplicate A because we need one copy to prove that R has type frozen A, and we need one copy because we haven't written consumes here. So we need to preserve the fact that X has type A. But that's a bit technical and not central.
No, I kind of understand. If it's frozen, it has to be duplicable, right? It says up there.
Well, it doesn't have to be duplicable for these 2 lines to be well typed. I think it has to be duplicable because we want to share the frozen cell between many readers. So that's why we want it to be duplicable. But these 2 lines would be well typed, I think, even if frozen was not duplicable.
But how do you know? I mean, you know that X is duplicable.
Yeah, X has type A, which is duplicable, but I don't know if that's central. I don't think it's central.
You could remove duplicable A.
Here, I could remove duplicable A. I would have to write consumes X colon A, and then it would still be well typed. I think I could do that if you want to try. I may have the code at hand. Let's see. The code is here. So here I should be able to remove that.
Then you need to remove duplicable.
So just try to type check that. So this doesn't type check. I don't know if the error message is readable. So what does it say? Could not prove R at frozen A. Well, it's a bit short. It doesn't tell us why. But here sorry?
Maybe the definition of the data frozen.
Yeah, there are several.
Up in the definition.
Okay, so you want to remove this here. And here, we get a mistake elsewhere in get. But that's normal because get duplicates A precisely. Yes. So, okay, so now it's saying, yeah, so it's okay to have a mistake in get here because get precisely duplicates the content. So I can try to fix it like this. Yeah. So now the implementation is well typed, but I haven't updated the interface file, so there is a mismatch between the two. Does that help? Yeah.
Yes, so frozen is duplicable, but not what inside.
Oh yeah, here frozen is duplicable. Oh yes, maybe that was the question. Yeah, so the type checker has to check that frozen is duplicable because we declared that to be the case in the interface file.
Yes.
And here it is duplicable because I included that constraint here.
So the fact that frozen is duplicable enforces or requires that A is like
yes.
duplicable.
Yeah. If I remove this, then the type frozen A is no longer duplicable because we don't know what A is.
Okay, so we should keep it.
Yes. Or you should change the interface file, but it would be more complex then. If you want to read once, then you don't. Yeah, then I guess you don't want to make frozen duplicable in that case.
But that means that the type checker will enter into the structure to check that everything is duplicable if you are externally duplicable. Is it something like this? Like if you have a list?
Yeah, there is a rule. There is a set of rules for deciding whether a type is duplicable. And indeed, for something like a pair, it's duplicable only if the two components are duplicable and so on. And for a list, for instance, the type checker will find by itself that list A is duplicable only if A is duplicable. Okay, so I could say a bit more about algebraic data structures, maybe, but we have seen much of it already. Or I could perhaps go directly to sharing mutable data. I think I will try to say just a few things about algebraic data types, and then go down there. So we have seen many of the principles. We have seen that you can declare a type like this. We can have several branches and several fields if you like. So that's the immutable type of lists. And you can add the mutable keyword and you get a type of lists whose spine is mutable. And the elements have type A, so depending on how you instantiate A, they could be immutable or mutable. And the only thing that we haven't seen yet is that when you match, then there is something which we call permission refinement. You get information by matching, as you may imagine. So if I know, for instance, that initially X is a list, a mutable list here, then when I match, I'm going to get more precise information inside each branch. So I'm going to replace this permission with something more precise. In the first branch, I'm going to get X's at m_nil. So this is a structural permission where I have the tag and 0 fields. And in the cons branch, I have a more general example where we have a tag and 2 fields. So here we know exactly what the structure of this memory block is. And what the type checker will do automatically is introduce names for these 2 fields, because it's pleasant and actually important to always have a name for every value. So we're going to introduce a name H for this field and a name T for this one. And to do that, we explode this permission into 3. So I'm going to say that head has type singleton H, and H is an A, and same thing for T. So now I get 3 disjoint permissions. And this isn't very pleasant to read, so we have some sugar for it. We can just say head equals H and tails equal T. So this is syntax which the programmer has access to if desired. So the programmer too is able to write these kinds of precise descriptions of the heap if necessary. And what happens next is that we're going to read that field axis.head here. And checking this access is easy. We know that axis is a const block, so it has a head field, so the read is safe. And furthermore, we know what the result will be, because we already have a name for it. We know that the result of the read will be H. Even though we don't know what H is, it's a name for that value. So we know that the expression axis.head will produce the value which we already have named H. And this means that after this read, what we get is just one new equation, x equals H. So it doesn't change the structure of the heap. It just gives us one more equation. That's inspired by alias types and also by separation logic. These are not new ideas of ours, but what's new here is perhaps more the integration with ML algebraic data types and ML polymorphism and things like that. Yes?
Doesn't that make your internal types quite big and your type inference quite slow?
Yes, it's true. The types are big and the type inference is slow, not so much because types are big, but also because sometimes there are several ways of trying to prove that a program is well typed, and the type checker has to explore, and that's quite costly. So that's one difference here with traditional separation logic for C-like languages. You see many papers where people have records and null pointers, which are typical in C. And then they have an inductive predicate for lists, which says a list is either null or a pointer to a block. And instead here we have algebraic data types. So a list is always a pointer to a block, and it's the tag that tells us whether it's nil or cons. So this is slightly higher level and easier to deal with for us. Yeah. So I'm going to go rather quickly through this, but I have some slides that show how to type check something as simple as the length function on lists. So the type of the list length function is pretty short as an ML, but the reading is a bit different. You have to read this kind of type in terms of permissions as shown here. This means that the caller must have permission x's at mlist_a if the argument is named x's. And after the call, they will get this permission back because the consumes keyword was not used. And they will get a new permission for the result, which has type int here. So if we look at the code, I'm not going to go through it in detail, but basically the permission for the list will be deconstructed as the calls are made, and it will be reconstructed when the calls return. So there is a rather intricate business of exploding and unfolding permissions as we go down into the recursive calls, and then recombining and folding back as we go out, as we return out of the recursive calls. And there is also some interesting framing going on. One thing which you may notice, and I have one special slide about that, is that this is really a loop. It's a tail recursive function, so it's going to be compiled down to a loop, because Mezzo is compiled basically to OCaml by erasing the types, and then OCaml will compile this to a loop. So it's an efficient version of the length function, and it's very easy to type check. The programmer only has to declare the types of the arguments, and that's it. But if you look at a proof of this in separation logic, what you may find is that people will declare that there is a list in front of us during the loop and a list segment behind us, and the loop invariant will be a conjunction of these two things. And there is some rather complex reasoning to explain what's going on as one block is moved out of the list in front of us and into the list segment behind us. And here this doesn't happen because the function is written in recursive style. So what we get is recursive reasoning, which is easy, thanks to the frame rule in particular, but at the same time iterative execution because we're compiling down to iterative code. So in a way we're cheating because we are reasoning in a high-level style and compiling in a low-level style, but that's good. I think it's a good kind of cheating. And now I will maybe take questions about that and skip ahead to how one shares mutable data structures.
Would it be conceivable to use that length function to compute the length of an immutable list?
No. At the moment, we don't have this kind of polymorphism. So the type list and mlist are completely separate, and we cannot reuse the same piece of code for both. We have thought about it, and I'm not completely sure whether it would be feasible. We have done it for arrays as one particular special case. We have a type of arrays which is parameterized with a mutability flag. So we have immutable arrays and mutable arrays as two special cases of the same general case. And this allows us to write functions which work over both kinds of arrays. But for user-defined data types, I wasn't quite sure, and we just didn't do it because we had enough complexity to deal with. So I'm going to skip to how one shares mutable data. So the examples that I'm skipping involve more functions on lists, like list concatenation and two flavors of concatenation. And you can look at them in the slides which are online. So now there are several ways of sharing mutable data. And And I'm going to review 3 of them. I think these are basically the 3 ways that we have at the moment, although one could conceive more of them. And the first 2 are basically alternatives. They serve the same purpose, but one is purely static and the other involves runtime tests. So there are different trade-offs in terms of conceptual complexity and runtime cost. And the third mechanism, which is locks, serves a different purpose. So it's going to be used in conjunction with the above 2. So I'm going to begin with nesting in regions which are traditional, so to speak. You may already know about them. So I will review it quite briefly. Nesting is perhaps less known, but it appears in several papers by Boyland. I have cited the latest one here. It's in Topless. And it's a mechanism for organizing permissions into a hierarchy. And that hierarchy grows at runtime, so to speak. So you can declare at runtime that a permission becomes nested in another one. So that's monotonic in the sense that once you have nested, you cannot undo the nesting. And it's purely static in the sense that you don't need to do any runtime tests and you don't need to actually represent this hierarchy at runtime. So nesting is a bit difficult to explain, I think. So what I will do is explain a slightly simpler notion, which is regions. And regions can be defined using nesting. So they're almost as general, I think. So what I will do is explain regions quickly. So we have added nesting in Mezzo, but we haven't proved that it's safe. So we have a special file with a few axioms that say what you can do with nesting. So regions can be defined using nesting. And they are very much like what you have in Haskell when you use the ST monad. So you may know that there is a type which looks like this in Haskell. It's a type of a reference that inhabits region rho and contains a value of type A. And a region, it's just a name, actually. It doesn't have to exist at runtime at all. It's just a name for a group of references. So in Mezzo, what we do is we have this abstract type of regions, and we have a function new region, which produces a new region, but it doesn't actually do anything at runtime. Internally, region is just defined as unit, and this just returns the unit constant. So the whole point is just that you can write let row equal new region, equal to new region. And if you do that, then you have a fresh name row. That's the only thing which we're trying to achieve here. Oh, you have a fresh name row, and you have an affine permission row at region. So even though the type region is defined internally as unit, I'm not declaring that it's duplicable. I'm not publishing that fact. So the type checker views region as an affine type, and this means there is a unique owner. This permission here is affine. So every region has a unique owner. And now we have the usual 3 functions for creating references, reading and writing. And each of them requires row at region and does not consume it. So you can think of row at region as a token which proves that you are the owner of the region. And you have to thread this token through your calls to new ref, get and set. So these are basically the same types that you have in Haskell in the ST monad, except here we don't have to use the monadic combinators. One way of explaining the ST monad is that it's a way of making the state linear even though you don't have linear types in Haskell. So it's a way of hiding the state from the user so they cannot duplicate it. And here, because we do have linear types or affine types in the language, we don't have to hide the state. So we can explicitly thread this token through the computation. So in a way, this subsumes the ST monad. Yeah, I guess that's what I wanted to say about regions. So this is a fairly nice mechanism in a way, because it allows you to group your references in several regions. And what I forgot to point out is that this type region inhabitant, ref, is duplicable, which is very important. It means as long as you put your complicated data structure inside a region, you're free to create multiple pointers to the same thing. You're free to have aliasing in there, and it doesn't create any problems because you have just one ownership token for the whole region as opposed to one ownership token per block, per memory block. So here when you have row at region, you can access any reference in the region, and there is no problem if there is aliasing between several references. So that's one way of sharing mutable data structures. And you could define a type of graphs, for instance, with arbitrary pointers between nodes, provided you put all of the nodes inside the same region. And then you have just this permission here, which serves as a permission to access the whole graph. So the good thing about that is that there is no runtime cost to regions. This permission row at region is passed at compile time. It doesn't have any runtime overhead, and there are no dynamic tests. But there are restrictions to this approach. One is that get is restricted to duplicable elements. Going back to the previous slide, here there is this sneaky constraint here, duplicable A, which says you can read a reference only if its content is duplicable. Because again, when we read, we are duplicating the pointer to the element. A region is basically a container, and so this is an instance of the problem that I mentioned earlier, where you cannot borrow an affine element from a container. Or you could try to have a mechanism for taking one element out of a region. It's called focusing in the literature, as in Fendrich and Deline's paper, Adoption and Focus. So you could do that, but then you get a region with a hole in it, so to speak. And later you have to plug the hole, and so you have to have a more complex machinery for proving at compile time that your code is correct. And another reason why regions are not very flexible is that they're monotonic. You can make an element an inhabitant of a region, but then it remains an inhabitant of the region forever. You cannot take it out. And this can be a problem in some practical examples. For instance, if you're implementing a FIFO queue, all of the elements of the queue are in a region. So when you insert, you put them in the region. And then when you retrieve an element, you would like to take it out of the region. And you cannot easily do it because these regions are monotonic. So this leads me to adoption and abandon, which is something which Jonathan and I introduced, I think, which is a version of regions with dynamic tests. So it's going to be less precisely typed. There will be potential for errors at runtime if you don't know what you're doing. But in return, we get a simpler static type discipline, which is relatively easy to understand. So one way of thinking of how we came to it, is something like regions that exist at runtime. So you may think of old work, which I'm thinking of Tofte's work, for instance, or Talpin and Jouvelot, where they had this stack of regions where you would allocate memory. And that's not what I'm thinking of, just to make things clear. In Mezzo, we have a single garbage collected heap. So when I say region here, I'm really thinking as a unit of ownership, something for which you have a unique token of ownership. So what if these regions existed at runtime? It would mean that a region would be something that maintains a list of the members, at least in a simple-minded implementation. And just to clarify or to adopt a new vocabulary, we prefer to speak of adopter and adoptees, so there is no confusion with static regions. So the adopter will be some kind of object that maintains a list of adoptees, and obviously. Adoption means I'm adding an adoptee to the list. And I will have another operation which is symmetric or almost symmetric. Abandon means take an adoptee out of the list because I want to use it. And abandon will involve a runtime check because we will have an instruction saying something like take x from y. So the syntax for abandon will be take x from y. Y will be the adopter. And x will be some object which we think is adopted by y. But we're not quite sure, actually, because as we will see, the type of x will not reflect who its adopter is. So we, as the programmer, think that the adopter of x is y, but we don't know for sure. So we will use this special instruction, which will check at runtime that x appears in the list of adoptees. If the check succeeds, then fine, we just take x out of the list and we continue. And if it fails, then the program stops, basically. Or you could try to do something else. But in the simplest case, let's just say that it's a fatal error. So this will, I haven't explained the details yet, but the idea is that this will remove many of the difficulties with static regions because I have these two operations, give and take. I will have the symmetric operation, give x to y. So I can adopt and I can revoke an adoption relationship. So it's easy to put things into a region and then take them out later. So focusing obviously becomes trivial. It's just taking and giving back. And you can focus on multiple elements too. If they are distinct, everything will be fine. And if they're not distinct, then you will fail at runtime. Yes?
Can you give x to several regions?
No.
So you have to check that before giving it that it does not belong to.
This will be statically enforced. We will see that we will have a kind of permission to give. And that permission will be affine. So we will be able to give an object only to one adopter. Yeah. So that's the runtime model. Oh yeah, the runtime model is actually the converse of the naive model. So the naive model is each adopter has a list of its adoptees. But that's not efficient because when you take, you have to search the list of adoptees looking for x, and that would have linear cost. And fortunately, we can just do it the other way around. We can have, because Basile mentioned, each object can have at most one adopter. So we can just let the adoptee points to its adopter if it has one, or just point to null otherwise. And this means we can implement give and take like this. Give is just write the address of the adopter into a special field. So every object needs to have one field like this, one adopter field. And taking means we test at runtime that the adopter of x is indeed y. And if that is the case, then we now consider that x is no longer adopted. So we write null into this field. And if the test is not successful, then we just fail at runtime. So that's the compilation scheme, if you will. The translation to OCaml is just that. And I guess now my plan was to switch to a demo to explain in further detail how this works. I hope you're not too tired yet. What I have here is a naive version of a graph implementation, which I'm planning to fix using adoption and abandon. Is this large enough? Yes? So what I have tried to do here is define a type of graph nodes which are mutable. So each graph node has a content field which contains some value of interest to the user of type A. Then there is a field visited, which is used for depth-first search, for instance. And then there is the neighbors field, which gives us the outgoing edges of that node. So I can declare this type, and that's fine. It's going to be accepted by Mezzo. I can also declare a type of graphs as an object that contains a list of distinguished nodes, the roots, and that's also accepted. The trouble, as the comment up there suggests, is that this is understood by the type checker as a type of trees, actually, not as a type of graphs, because node is affine. So list nodes means list of disjoint nodes, and the whole thing is really a type of trees. It's not a type of graphs, as one might think. So we can even go as far as write, maybe we can not realize that we have a problem, and we can write a definition of DFS, which a recursive definition where we visit the graph and mark the nodes as visited, and this is also accepted. But actually the marks serve no useful purpose in that case, since we are just going down a tree. Sorry? Oh, iter. Yeah, iter is equal to list iter, actually, because the neighbors has type list of nodes. So what I'm saying is that on each element of this list, you should call visit. So yeah, this I could, where is my cursor? This I could write list colon colon iter. Okay, and now we discover that we have a problem when we try to construct a cyclic graph, which is what I'm trying to do here. I think I'm trying to construct a node that points to itself. So I can allocate my node n and initially say it has no neighbors. So here I'm using the unit value as the initial value of the neighbors field, which is accepted because the types which you choose for the fields don't have to match the definition of the type graph, at least not in the intermediate states. They have to match at the end, because I have claimed that at the end G will be a graph. But I can initialize neighbors with the unit value and then try to patch it. So here I'm trying to patch neighbors by writing ns into it. And ns is a singleton list of just n. And so I'm constructing a cycle in the heap using the usual patching approach. And this is okay, actually. One might think that the type system will find a mistake on the assignment, but actually no, the assignment is fine because our singleton types and structural types are precise enough to describe the cycle of length 1 which we're building. So that's not a problem. And even actually constructing the graph is still okay. So the mistake really, the type error really occurs on the very last moment when the type checker tries to verify that this graph has the type graph int that was declared up there. Because then what happens? We need to prove that ns is a list of nodes. Yeah, and it's not a list of nodes because to check that, we need to trace down the definitions and we need to prove separately that n is a node and n.neighbors is a list of nodes. And that's not going to work because the same node is being used twice in that claim. So it would work if the type node was duplicable, but since it's an affine type, it doesn't work. So I'm sorry I'm a bit short on time, but I'm hoping to be able to fix this example in the remaining time. So, so what do I do? Well, I need to fix that by changing the type node A here. I cannot declare that I have separate nodes in that list. Actually, I don't, because I want this to be possibly an arbitrary graph. So I want to allow the same pointer to appear several times in that list. And I also want to allow cycles. So here I need to put a duplicable type, whatever. It has to be duplicable. What we do here is that we have a special type for that, which is produced by which will be produced by the adoption instruction. So the type of X after the adoption will be dynamic. And you can think of dynamic as inhabitant of some region or adopted by some adopter, but there is absolutely no static indication of who the adopter is or what the name of the region is. So here I'm just saying it's a list of adopted objects. And that's a duplicable type because there is no danger in sharing this very weak information. So I can declare this. And similarly, I guess here I should declare that we have a list of dynamic. So now I need to fix my definition of DFS, which I haven't really commented, but what's going to happen is that n will have type dynamic here. And if I try to type check that, obviously I'm going to get a type error. Yeah. If n has type dynamic, then I cannot possibly read the visited field because that would require n to have type node. Or in other words, I need to prove that I am the owner of n, or that I have the right to access the node n. And at first here, I don't even know that n is a node. All I know it's adopted, or maybe adopted by some object. So this is where I have to use take. I'm going to say take n from, and actually from whom. I haven't said that. I'm going to adopt the convention that all of the nodes in the graph are adopted by the graph object itself. So I'm going to use G as the adopter of all of the nodes. So here I'm going to say take n from G because I will ensure that the nodes are adopted by G. So take n from G. So this only requires n to have type dynamic. And it will check at runtime that n.adopter is G. And if that check succeeds, then we will learn that n has type node. And how do we learn that? Because we declare it. I will declare that the graph adopts objects of type node A. So for each adopter, it can adopt a single type of adoptees. And the programmer is allowed to declare what type of adoptees that is. So that take instruction requires n at dynamic before the instruction. And after the instruction, if it hasn't failed, I will get n at node A. I will recover the ownership of the node. Before the instruction, so to speak, n is owned by the graph. And after the instruction, n is owned by me, so to speak, or by the currently executing thread. And this should allow me to access the node as before. So I can read and write this field. I can read n.content. And
you should give them.
Yeah, sure, I should give it back. Otherwise, I'm going to be in trouble. At this point, when I recursively call visit, visit is going to expect that all nodes are adopted by the graph. So I need to put it back in the graph before I do the recursive call. So I'm guessing I should call give here, give n to G. And I guess there should be also an else. I need to return it whatever happens. So if I'm not mistaken, it should be something like this. Let's see what the type checker thinks of that. Oh. Now that is what is going on. This expression cannot adopt. The only permissions available for it are... I cannot read the end of the message. Maybe I should re-zoom my window. Oh, dynamic equals G unknown. I seem to be missing a permission for G. Oh yes, G. I have no permission for G. That's the trouble. Yeah. Here I know that G is a graph at the level of the outer function, but in the inner function I don't know that by default. And if I want it to be the case, I have to declare that visit needs the permission G at graph A. So that's it's a good and a bad side of the language at the same time. Every function has to be explicit about the permissions that it needs. And in the earlier version of the code, visit didn't need any permission for G, whereas now we're going to need this permission because G is the adopter, and the take and give instructions need the permission for the adopter. So it's still not over. Oh, I cannot read n.neighbors. I need to lift this above the give because it's too late to read n after giving it back. And this is okay. So the DFS here looks okay. And then I should fix the construction of my cyclic graph. So is there anything to fix? Yes, I need to give the node to G. So here, this is another problem. If I forget the give instruction here, no error is signaled because the type checker doesn't know that I meant to give all of the nodes to the graph.
But the graph is at runtime because it can't fit.
Yeah, then the first DFS will crash if I forget to give the node. Yeah. So I have to say let G is graph in and then give n to G and return G. Sorry?
N to G or G to G?
It's give n to G. I'm giving the node to the graph. My convention is that all of the nodes are adopted by the graph. And there is a last thing. I guess I need to annotate graph int here. It's a limitation of the type inference. Yes. Yeah, so this should work. I haven't set things up to actually run the example, but that's how you fix it. So I'll conclude here for today. Maybe I'll jump to the conclusion slides that I had planned. Is this the right? No, it's not the right file. So I'll save locks for tomorrow. And what did I want to say? Yeah, some related work that I will maybe mention tomorrow. So what's new here? You may have recognized a lot of things that you knew already from separation logic or alias types or other previous work. So one new thing is that we're trying to design a high-level ML-like programming language. We don't want people to use null pointers or iteration. When we want them to have GC and first-class functions. So it's really ML, but with a different type system. And we hope that this is a better conceptual framework for structuring your programs, because it's a framework that's imposed on the programmer when they write the program. So they have to think about these ownership problems when they design the code. And this might help design more reliable programs, and it might also help prove the programs correct more easily, although these claims have yet to be substantiated. So I'll conclude for today with that quote, which is one of Jonathan's favorite quotes. We are, maybe by 1984, we will have a consensus for a really good programming language. So maybe you know that quote. That was Don Knuth in '74. So I think the conclusion is that there is still a lot of work today to be done to design good programming languages, and I'm not expecting that to stop at any time, but I'm hoping that we will be able to make good progress in the near future, and we have made good progress in the past decade, for instance. Thank you.
So 30 years later, are there questions or comments?
Well, an implementation question. Today you're using Poincaré as a object language again. Yes. But is your region the same as region in garbage collections? I mean, could they know?
No, so we need a GC, just like OCaml needs a GC. So our regions...
Could you use a new GC region-based with your region mechanism? Or is it not all the same?
It's not really the same. Yeah, our regions are units of ownership, so to speak, and it's not necessarily easy to map that to actual regions in the heap. For one thing, we have duplicable objects which are not controlled at all. They could be allocated anywhere, and their lifetime could be completely arbitrary. And for mutable objects, we have some more control, but because of things like this dynamic type, we again don't have a lot of control concerning the lifetime of objects and in which region they are allocated. This type doesn't tell us anything, so it's hard to use the type information to drive garbage collection, for instance.
And another question, you didn't mention any obj magic trick. Do you have one?
Oh yes, sure. When we compile to OCaml, we just... in Mezzo. Yeah, we also have a magic primitive which is analogous to OCaml's. We don't use it in user programs. We do use it in some... When we axiomatize nesting, for instance, we just say, okay, that's the type of the nesting operation. Yes?
So you compile to OCaml?
Yes, but compiling is a big word. It really just means erasing the Mezzo types, basically, putting magic everywhere, because Mezzo is incomparable with OCaml in expressive power, and compiling give and take in the way that I showed, and basically that's it. And one thing which we're missing is that Mezzo on paper has concurrency and locks and threads, but OCaml doesn't have them. So at the moment we don't have this aspect.
So I have a question about you were showing your graph exploration.
Yes.
And I was surprised by the fact that in the end you said you need to remember that you will. Your graph needs to adopt all its nodes.
Mm-hmm. Oh yeah, that's in the head of the programmer.
Yes, and this
yeah.
is not detectable, yes, by the type. Type inference. Because it worked, and then you said, "Oh, I should remember
yes.
to attribute." So I was just wondering whether
yes, the trouble.
An intrinsic problem there, or
well, the type checker knows that any adoptee of the graph must be a node, but it doesn't know that every node must be adopted.
So you mean the idea is that there are nodes around, but they don't know necessarily which graph they are.
Yeah. Yeah, you could actually take one node away from one graph and then have it adopted by another graph. So it's basically.
So the fact that the nodes, so if you go,
yeah.
The nodes. Because the node. Okay. The point is here. The node is pointing to itself. Yes. So you removed it and.
What do you mean? Are you speaking of the general DEFS?
No,
or the cyclic graph?
Yes. When you build
yeah. So the cyclic graph is.
So it's
further
your last
down.
node.
Yeah, if you forget to give it to G, then it's a node that's not registered, so the DFS will fail. And one thing which I forgot to mention is, yeah.
No, but still you're saying G is a graph where, sorry, when you go down, when you build the cyclic graph.
Yes.
Just to understand. So you start from the empty.
So I'm building the cycle, then I'm allocating the graph, and then I'm registering this node by saying it should be adopted by the graph.
Yes.
But if I forget that give, it's not detected.
It's not detected at compile time, but it crashes at runtime.
Yeah, it will crash when you try to call DFS.
Sure.
Yeah. So in a way, it's
hard to detect these things statically.
Yes, statically. Well, if you had a purely static region system, you could try to declare that here, each of these things is a node which is adopted by this graph eventually, and so. But this would make the types even more dependent. And actually, you could play around with that in Mezzo. We tried, but there was so much dependency that it became very difficult to name all these objects and keep track of the dependencies between them. So Mezzo is a kind of dependent type system, but not a very powerful one. So it's nice to have some dependency, but not too much.
And here the dependency will be on the graphs or on the...
Yeah, here you would need to say these are nodes. Here you would need to say these are nodes adopted by G, where G is this object. And actually you can sort of say that in Mezzo today, but it doesn't work very well.
Okay, so they're like, in the end, they will be adopted. Yes? So they're
so here,
around
here you would really need a comment here saying adopted by this graph, and then you would have to informally make sure that this is enforced.
Thank you. Yeah. So that's it. So let's thank François again.
Thank you.